All right. Hi, I'm Aaron. This is Georgina. We're both part of the Nanoscale Design and Manufacturing Lab here at UT. We work with Dr. Michael Cullinan. Today we'll be going a little bit over the Microscale selective laser sintering project. So here's an overview of the system. On the right over here, we have a slot die coating system, which lays down a thin layer of nanoparticle ink. Right now we're using copper and silver. That's laid down onto a substrate, which rests on top of this nano positioning stage here in the middle. This helps us this gives us XY control during sintering. That helps us do things like align each layer, as well as expand the range or area in which we can sinter in. So this stage is then shuttled over to the optical subsystem here on the left. And that just consists of a DMD and a set of lenses that focuses a desired pattern down onto the layer of ink that was previously deposited. And so this process is repeated several times until a desired part is created. So some of the applications of this technology, one that we're particularly interested in is the fabrication of interconnect structures in semiconductor packaging. And this is because they're moving towards finer pitch and higher aspect ratio structures. Some other applications that we're looking at include MEMS, microscale medical devices, or lightweight structural elements such as this lattice shown here. So most of our experiments or parts that we've been able to fabricate have been done on glass slides as our substrates. We've also done some parts on silicon wafers with different coatings in the past as well. There are a couple of examples of dot arrays here at a couple of different pitches and diameters. We also have this Longhorn, which notably has a feature size or minimum feature size of 10 micron at the tip of the horns. And also here we have the NDML lab logo. And so one of the major challenges to creating these nice looking parts is understanding how the heat spreads during this process. Currently, one of the challenges is actually we're seeing parts that are outside of the laser exposure that are either partially sintered or fully sintered. And that's just due to the heat transfer from the surrounding. So Georgina will be speaking a little bit more about the simulation side of that to kind of understand this problem. So.
Thank you. Okay, so as Aaron mentioned, one of the major challenges that we face is achieving near net shape parts because of the heat affected zones that form during sintering. And so to try to solve this issue, we're looking at modeling the Micro SLS sintering process. So there are two main advantages to modeling the sintering process. The first is what we've discussed, which is in trying to correct for the heat affected zones that form during sintering. So if we can predict how the heat affected zones are going to form, then we can make in situ corrections to the laser heating profile to account for how heat will spread. And this would get us more towards the direction of achieving near net shape parts. The second advantage is that if we're able to predict the physical, electrical, and thermal properties of the manufactured parts prior to printing, then we can specifically optimize and design our sintering process parameters to yield the properties that we'd like to see. And so to achieve these goals, our modeling process is broken up into two main particle scale modeling efforts, which feed into each other. The first is modeling solid state nanoparticle sintering, and the results of these simulations feed into the second modeling effort, which is modeling the thermal conductivity of the powder bed. So the knowledge that we gain from the thermal conductivity will allow us to calculate new thermal profiles, which are fed back into the solid state sintering models, and it just cycles through. So now I'm going to go into a bit of detail on the modeling efforts. The modeling of the solid state nanoparticle sintering is done using a phase-foot modeling approach, which where the sintering is driven by the minimization of the total energy in the system. And this total energy is a function of the bulk free energy, the interface energy, and the grain boundary energy. So this slide shows a video of the simulation applied to a 2x2 micrometer bed. what we can see in this video is that we have initial stages of rapid neck formation between the particles, and then the necks grow and we see densification and shrinkage. So the evolving particle configurations from beds such as these are passed into thermal simulations to calculate the thermal conductivity of the powder bed. The thermal simulations use a 1D approximation of steady state heat flow, where heat flux is applied on one end and the other end is held at a constant temperature. And so to calculate the thermal conductivity, we use the 1D approximation of heat conduction using Fourier's law, but modified to account for the non-uniform surface area across the primary direction of heat flow. And so using the Sintering simulation and combining that with this, we're able to get curves that relate the thermal conductivity to the density of the powder bed. And so the end goal with all of this is to use these particle scale, thermal, and sintering simulations to inform a larger bed scale model, which will be able to make predictions of the temperature in the powder beds, as well as predict the final properties of the sintered parts. So that's it. Thank you for listening. And we will be at the back with posters and also get questions now.